Hi, everyone. Okay, today I would kind of call our official beginning to our applications unit. So today is where we're going to start to go through from start to finish, create a function, create an equation, solve the problem for whatever they're asking. We're kind of putting everything together that we've examined over the course of the year. So, as you're working your way through today, make sure that you pause the problem to give yourself time to go through and read that problem in detail. We're going to jump through and we're going to talk about some look-fors, some strategies, and overall problem solving. So, pause the video now, give number one a read. Okay, and we should be back. Now, when you take a look at problem one, we need to be able to break down that problem. And quite often, one of the strategies is to look at what the question is asking you to find first. So the question is asking us to find the dimensions of the screen, and we have some rounding rules in the end. So the job then is to come up with the dimensions of the screen. So what shape are we talking about in that screen? Well, if it's a television screen, we're talking about a rectangle. One of the other strategies that we want to use is if you have a measurement problem, a problem that requires a shape, then quite often we should go through, draw a picture. Now, if I was to create that diagram to represent that picture, maybe there's my television screen. You have two options every time you go through to solve. If you're going to use a variable, we have to define that variable. And one of those options would be to let's just say X for generic terms, represent the blah, 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 blah. But because this is a measurement problem, drawing a fully and properly labeled diagram does just as good. So I'm going to get rid of that let statement because I'm only going to write out a let statement if I need to. Because it's a diagram problem, I'm going to label. So I'm going to label everything I can. The label has a diagonal that is 54 centimeters. The width of the screen is 15 centimeters more than the height. So here's where I get to a decision. Maybe I end up saying my width is going to be X. And since the width is 15 greater, then my height must be X minus 15. However, if I had to give maybe a suggestion that instead of going through and dealing with something and something less, what a lot of people tend to do is they like to start off with defining the smallest thing as their variable and then building up towards that. So, key thing for us to understand is either one of those labels for those two shorter sides are good. We would just be solving for two different things. So I think the common approach, if I had to make an assumption just based on history, is that I would have a lot more people that would choose to label maybe the height as X or H, and then the width being 15 greater and building onto that. Now that we have a labeled diagram, it's time to jump in and use what we know. So you take a look at that diagram. That diagram is a rectangle. I could work some information with a rectangle. I could calculate the area of a rectangle, the perimeter of a rectangle. However, hopefully it's jumping out at you that you also notice that by forming that diagonal, you actually form a right triangle. And you do know all three sides of that right triangle. And so I'm hoping then when we go, hey, triangle, and we think about all the things that we have at our disposal for that triangle, the first thing we would consider, since it was a right triangle, would be Pythagorean theorem. After Pythagorean theorem, then we can consider some SOHCAHTOA stuff. But let's always go back to basics. And so, since I have all three side lengths, I know that the square and the square of the two shorter sides added together has to give me my hypotenuse squared. And now you've built an equation. We should be good. So key thing is what I have written in blue defines the problem. What I have written in purple, there's your problem solving. Now that you have that down, we should almost be able to shut off our brain and be able to crank through where we need to go next. We recognize that we have an equation, and we can solve that equation for x. We can do that relatively easy by expanding those brackets, multiply them together and double it, square the last. I'm going to have to push some buttons on 54 squared, and I get 2,916. Now that I have that, I can collect like terms. I clearly see that I can't put my x's together into one term, and so that means I'm moving everything to one side and beginning. Now, here's where I would argue we do get a little bit more problem solving in a way. That you do get down to this point, and to finish off solving that problem, you have to make a decision. Do you want to spend some time to try to look and see whether that factors, or perhaps we just go through and say, okay, I'm going to go through and I'm going to use quadratic formula because that's going to be faster. So I have my negative b plus or minus the square root of my b squared plus, okay, now I'm going to have something pretty big. I've got my 4 times my 2 times my negative. You'll notice that I put that plus down right away because the most common mistake is going to be to forget that that c value is negative. We should be automatic with that by this point. We shouldn't be making any mistakes in that regard. And we're getting down to a big product at the end. And then that's all over 2a. Now we can simplify what's underneath that root. And so when I add that together, I'm going to get 22,428. And now, like we discussed before in the canned problems, since you're solving an application question, you do not have to solve for a fully simplified exact value. It's okay to round off in an application setting. Just make sure that we don't calculate the root of 22,428, round it off, and then round off again. So we're going to go through that process, and you're going to crank out the most exact answers you can get. So the first one, negative 30 plus root 22,428 divided by 4. And my rounding rules say that I need to round that to the nearest tenth of a centimeter. So I should get then approximately 29.9. Or in the negative case, negative 30 minus that big ugly mess, I should get down to negative 44.9. So, a couple quick things. We get down to the end. We have to consider our solution. 29.9 centimeters, that makes sense. That's possible. Negative 44 as a height is not possible. So I'm going to make sure that I label that as inadmissible. Okay, did I fully answer the question? No, because the question asked me to find dimensions of the screen. We don't need to see how you get your calculations. Instead, you can just jump straight in on, we know that we are 29.9 centimeters by, and now I can sub that 29.9 into my width expression by 44.9 centimeters. Now that we got down to that, we've got a good solution. So let's just do a quick overview of the problem. First, since it was a measurement problem, we created our diagram. We were then able to create the equation that models that situation. You recognized it was a quadratic equation. Your mechanics took over. We made sure that we finished off the problem by including units and answering the question in full. So hopefully we were pretty good, and hopefully we feel confident moving forward with what we're going to see today. Okay, so now you take a look at problem 2 and do the same thing. Give it a read. So pause the video whenever you need to. Read that problem, make sure that we understand what we're dealing with. Okay, we should be back. So the first thing that we're dealing with, we notice we have a rectangular box. So I'm going to go through and I'm going to draw a diagram again to model that situation. That allows me to avoid creating a let statement and having to write out let x represent and so on. Okay, the question says a rectangular box is 20 centimeters high, so I can label that detail in there, and twice as long as it is wide. So here would be another instance where I think we would be much more comfortable. Since it says it is twice as long as it is wide, then we make the lesser dimension x, and therefore the longer dimension 2x. You could have, if you wanted to, labeled that box where the length was x, but then we would have had to deal with a width of 1/2 x, and now we're introducing fractions, which probably is going to make us slow down a little bit. We can avoid that by using the blue labels. Again, it does not matter how you choose to label it, but you have to make very clear what is x in the problem. My reader can clearly see that that's the width of the box. Okay, the question says that I need to go through and find the volume. So I know that the volume of that box would be length times width times height. So I could go through right now and sub all of that material in. And I can get down to 40x squared would be the expression for the volume of that box. My problem, though, is I don't know what the volume is. That's what the problem has asked me for, and I do not know what x is. So maybe then I stumble my way through the problem and I notice that the other piece of information given to me was that the surface area was 1600. Okay, I think we got down to a point where we should be able to pause this video and you should be able to finish off this problem. Maybe not confidently, but we should be able to finish it off. So again, as I said at the beginning, pause the video at any time throughout these problems as soon as you feel confident to tackle that problem. Okay, so we're going to jump in and we're going to use that surface area. So maybe I hop out of what the work I've done and I say, well, the question gave me surface area, so I need to come up with a surface area expression. Now, you would never have to show this line. I want to be clear because we don't need to see the formula. You could just use that formula. If we take a look at the box, we should be good that there's 6 sides and all of those sides can be paired up. So for instance, if I was to look at the top and the bottom of the box, that would be 2 of the length times the widths. That would be the top and the bottom of the box. But then I could also add to that my sides. Well, my sides, I would have 2 of those, and those would be the width times the height. Lastly, I would have the front and the back of the box. So I would have those gold rectangles. So I would have 2 of my length times my height. And there's your formula. Now, what you'll also notice if you examine that formula is you have every combination of length, width, and height included. Again, we would never have to see that. But if you like including that, feel free. Instead, what we can do is we can jump right into that equation. We know that the area is 1600. Problem told us that. And how do we calculate that area? We have 2 of the length times the widths. There's my top and my bottom. Then what I'm going to have to that is going to be 2 of my sides. That would be the width times the height. Then I'm just going to put brackets around this so we can look back at it closely. Then I'm going to have 2 of my front and my backs, which would be my length times my height. And again, you'll notice that I have every combination of my length, width, and height in that equation. Okay, you take a look at that purple equation that you have, and we should be good with how to solve it. So again, pause the video anytime where you're comfortable. Okay, probably we're going to take a step and we're going to go through and just simplify every term on the right side. So you got a 2 times a 2x times an x, so 4x squared. You got 2x times 20, there's a 40x. And you have 2 times 2x is 4x times 20 is 80x. You take a look at that equation right now and you notice that you are going to have terms where you can't collect your x into one variable term. So let's get everything to one side and let's write that in standard form. And so when we get down to that equation, you would be good to jump in now to try to solve that equation. However, maybe we work our way through and we say, okay, I can recognize that I have a common factor of 4 in all 3 terms. And so I'm going to divide out that 4 from everything. Okay, now we get to a point where we're looking to factor or formula, and maybe we can take a quick peek and we notice that if I have a positive 40 times a negative 10, then that will give me two numbers that multiply, that is an ugly M, that multiply to give negative 400 and add to give 30. We can then finish off the problem. Therefore, x equals negative 40 or 10. Clearly, the negative 40 is inadmissible. We cannot have a width of negative 40. And therefore, we can accept the 10 that is reasonable. Now, I don't have to put units on that 10 because what did the question ask for? It asked for the volume. And so maybe I take that 10 and I sub it back into my volume expression. Or maybe we just take a look at that 10 and we say, well, then my box would actually have dimensions of 20 by 10 by 20. And so you could calculate the volume of that by simply multiplying those values, and we get down to 4,000. Now that that 4,000 is my final answer, I need to make sure that I have units on it, and I have my centimeters cubed. Okay, we got another problem down. Let's jump in and deal with another. And so, like usual, give it a pause, give it a read. Okay, so we've read the problem. We can see we're talking about a rectangular field. And so if we're talking about a rectangular field, then I'm going to have my field. It says that the field is to be enclosed and then divided into two sections by a fence parallel to one of the sides. So if I was to then divide it into two sections, sorry, I made that jump, divide that into two sections, maybe I have something like this. Now, the only reason why I did that is my guess would be that I would have a bunch of people that wouldn't have gone through and put that on, but instead would have drawn this. And I want to make sure that we're all very clear that is completely acceptable. It just says that it's broken into two sections by a fence parallel to one of the sides. But I don't want us to think that we should be making the assumption that these two fields then are equal in size. Nowhere in the problem does it say that. So I need to make sure that I haven't made that assumption, and so I might just do this to really put it in my head that I know that they don't have to be equal in size. The other thing that I want to maybe address is that we could have had this scenario. There's nothing wrong that says that we had to break that fence and we couldn't have divided it into two longer ones, longer and skinnier maybe. It doesn't matter how we break that up, okay? Not at all. So what I'm going to do is I'm going to work my way through the blue and we can see how we can tackle the problem. Okay, the question says that we're going to use fencing that totals 600 meters. So that tells me then that every length of that field, if I add up all of those red lengths, I'm going to get a total of 600. Okay, so what I can do is I know that I can label my diagram. If I switch it back to blue, one of my dimensions I'm going to label x. So maybe I label that one x. Well, if that dimension is x, then I also know that this dimension is x and this dimension is x. Okay, now I don't know what the other dimension is. However, I should be able to come up with an expression based on the 600 meters of fencing. Let's see if we can follow along with this one relatively quickly. If I have 600 meters of fencing to go around that whole shape, then what's left over for the bottom side would have to be the total minus those 3 x's that we used up. Now, the issue becomes that's the amount of fencing that's left over for the 2 red sides. And so for me to get just the bottom dimension then, I would need to make sure that I divided that up by 2 to cut it into 2 equal parts. So for me to be able to work my way through, I have the total, subtract what we've used up, divide it among the remaining sides. Now, if that seemed a little unclear, then you could always have done this. We could have used 2 variables in this case. And we could have then said that what we have in this scenario is going to be 3x's plus 2y's that give you a total of 600 meters of fencing. And then since we wanted one variable, we could go ahead and isolate for y. And notice we come right in here. So if we're good with that other theory, then we don't need to introduce 2 variables, but rather we can just work our way through with 1. Okay, so we have our dimensions labeled on our diagram in blue. Now, the question asks me, what is the greatest area that can be enclosed, and then what dimensions will give that area? I notice that greatest is just a synonym, meaning maximum. So that's just another way for us to say, what is the maximum area? And one of the key things that we want to make sure that we're good with is to be able to work our way through the wording of that problem. So I'm just going to get rid of all that writing for a second. The question asks us for the greatest area. So that means maximum area. And anytime we need to find a maximum area, then we need to produce an area function. And so I have my area function. Well, how do I calculate the area in blue? Well, my shape is a rectangle, so I'm dealing with length times width. Well, I can sub in the details of that function. That is a length of 600 minus 3x all over 2 times a width of x. Now, one of the big parts that often jams people is that as they work through these problems, they get focused on the fact that you have an a on the left side, and they want to replace that a with a number. I actually don't want it to replace a number. Because the problem asked me to find the maximum area, that means I need an area function. I don't know the particular value of the area. In fact, as I change x, I'm going to get different areas for that rectangle. So what I need to produce then is an area function that gives me all my possible areas. Now, I have that area function. I'm going to simplify this, and I'm just going to write something in a certain way so we can see it. I'm going to expand that x in. And when I get down to that point, I just want to draw to your attention one key thing. Because we need to find a max area, we know that in a quadratic function, our max areas are found by using negative b over 2a. So if I was to jump down here and say, well, then I know for max area, my independent variable, in this case x, has to equal negative b over 2a. You might notice that that form that I have in the blue of the function isn't that useful. I want to have an isolated a term and an isolated b term. So even though it doesn't work out well, I'm going to take that divide by 2 and I'm going to divide each of the terms on top. So in this case, I'm going to get 300x, and then I'm going to have negative 3/2 x squared. And we normally wouldn't do that because of the fraction in 3/2. However, that becomes the most useful form for us. Now, I don't think we should get to the point where we have to rearrange that. We should be good that in the relationship negative b over 2a, our b value is the coefficient of your x, and our a value is the coefficient of your squared term. So I can then go through and say, well, then my x has to equal negative 300 over, and maybe we're pretty quick to just say negative 3. I've got 2 times negative 3 halves. My 2's will divide out. We come in there. We're then able to reduce that, and we can get all the way down to an x value of 100. Okay, here's where we're going to differ, and here's where we're going to kind of take different routes through. We now know the x value that creates the greatest area. But we need to answer the question, what is the greatest area, and what dimensions give the area? So maybe right now we go through and we find the dimensions. Well, you know one of the dimensions is x, and so that is 100. In the problem, we're talking meters, so I put all my units. By, now that whole field is a rectangle, so what's the length? We can just in our heads do a substitution in for that x, which means we're going to have 600 minus 300. That gets us 300. Divide it by 2, gets us 150. The reason why I found the dimensions first is because now to answer the next question, what is the maximum area? We can then say that your area is, and now we know it's length times width, so let's just multiply those together, and we get 15,000 meters squared. Okay, you didn't have to deal with it in that order. You could, of course, taken your x equals 100 and subbed it back into any one of those area functions to be able to calculate your area. However, I think finding the dimensions first, since the question asked us for that, is probably the most efficient way. Okay, I want to come back to one other thing that maybe can simplify some stuff for you. And I want to go back and I just want to draw a different diagram. So we're not going to go all the way through and solve the problem, because we already have, but I want to draw your attention to anybody that thought to do this as their diagram. Sorry, I want to make sure I don't go down the middle. I don't want to give the appearance of having it. And that's a horrible division. That's a little bit better. And then choosing to make this your x. If I had to give a suggestion, I tend to make my x value the side that appears most often. Now, the reason for this is because it means that when I go and find the other dimension, I'm dividing by less. So watch very quickly what will happen if I chose to create the green diagram, which is 100% correct. Okay, I need my dimension on my other side. So now I have my total of my fencing. I have to subtract the 2 x's that I just used up. But now I need to divide that by the 3 remaining sides. So very quickly, I would then have an area that would be x times 600 minus 2x all over 3. I go ahead and I expand that, and I get negative 2/3 x squared plus 200x. Now when I go through to find my max area, and I use negative b over 2a, notice my negative 200 over, now in this case, I have to divide by a fraction. That it just means that I got to do a little bit more work. Now, when I divide that, I know I'm going to flip and multiply, so I've got my 200 times 3 is 600 divided by, there's my 150. And notice that what you came up with was just the other dimension. You could then work your way back, and we don't need to do that. So the piece of advice I would give you, when you're trying to decide right back at the very beginning which side to label x, I tend to allow that side to be the side that appears most often. Okay, one more problem to go. Okay, there's our last problem. Let's pause the video, give it a read. Okay, we should be back. So this problem should sound pretty familiar, and in all likelihood, this was one of those tougher problems that you dealt with in grade 10. So as we take a peek, we notice we're talking about mowing a uniform strip around a rectangular lawn. I can tell it's rectangular because the dimensions are given. So I'm going to draw my diagram. I know that that would be 30 meters by 20 meters. Okay, it tells me that Stewie's going to mow a uniform strip. And so we should be good that uniform means the exact same. So it means same dimensions. So Stewie's going to go through, and Stewie is going to mow off a strip around the outside of that lawn that is the same everywhere. If the section of the lawn that Stewie mows, so I'm just going to highlight that a little bit, and I'm going to shade that in with red. So the red represents what Stewie's mowed. If the section that he mows is double the size of the uncut section, okay, I'm just going to highlight in the uncut section, and we'll label that as green. Then how wide is the strip? Okay, so a couple things that I noticed right off the bat. And one good problem-solving strategy can be that when the question asks you, how wide is the strip? Or if a question asks you, what is the volume? Or if the question asks you, what is the length? If the question asks, then a good strategy that you can try is to make that be your variable. So when I take a look at that diagram, I might make that distance be x. So that when I create a function or create an equation, when I solve for x, I'll actually have the solution to the problem that I've been asked. Now, the nice part is where that word uniform comes in. That because I just labeled that dimension x, then I know that that dimension must be x, that all of the widths of the strip must be x. Okay, at first that might go, okay, that doesn't really help us very much. However, I'm going to now go through and just clear out a little bit of space in the uncut section. Now, I erased quite a bit more than what I wanted to, so I'm just going to highlight in some of that again. But the reason for that is I can actually create dimensions now for the inside rectangle. That my original rectangle was 30 all the way across. And so then if I'm talking on the inside, I would have all the way across, subtract the 2 x's that I just mowed. My width, for the same reasoning then, would be 20 minus the 2 x's I just mowed. And those represent those inside dimensions. Okay, I'm just going to shade in the fact that that's all still uncut grass. Okay. We have a number of ways that we could go through and solve this problem. What I want to do is I want to maybe go through the exact translation of that English language into algebra. I would not say that this is your most effective way of solving this problem. However, it might be a way that we could kind of go through and we could directly translate. Okay, first thing. It says if the section of the lawn that Stewie mows. So the section, sorry, that just jumped. The section of the lawn that Stewie mows is double the size of the uncut. Double, and I'm just going to, the uncut. Then what I can do is I can take that sentence and I can translate it. So the first part I need is I need what's going to create the section of the lawn that Stewie mows. And maybe I can look at that then and say that's kind of like a donut question. That red shaded in region would be the whole thing minus the portion that was cut on the inside. That portion represents the cut section. Okay, that is then equal to, now it says it is double the size. is means equals. Now I need double, and I need the size of the uncut section. Well, the uncut section is that rectangle on the inside. And there is an equation that I could create that directly translates that English language. Now, everybody in here should be good to be able to go through and expand those brackets, collect like terms, and solve. Everyone should be good. However, I just want to draw to your attention a key mistake that can be made. Okay, the first thing we would do is we would multiply that. So there's our 600. We would then subtract off. Now I got to multiply my binomials. So I get a 600, and then I have a minus 60x and a minus 40x and a plus 4x squared. And then on the right side, I have my 600 double it, 1200. I have a negative 60. I can go a little faster, and a negative 40. So that's negative 100, negative 200. And then I have a positive 4 double it, 8x squared. And there's the expansion of that line. Can you see my mistake? It's so common for us to make, and it is going to kill you on a problem like this. Do you notice? Back here when I expanded these binomials, it says to subtract the product. And I did not do that in purple. That only with these brackets in did I now do that. But that mistake is so easy to see, we see it all the time, that maybe there's a better way to solve the problem. Again, let me reiterate, everybody should be good with all of that algebra to work their way through. But I'd like to talk to you guys a little bit about using some proportions. So I'm going to draw a different diagram. I'm just going to make it a little bit bigger, but you're going to notice that it's going to model the same situation. And what I want to talk about is proportion. That you can use proportions to simplify the equation you build. Okay, how can we do that? Well, let's take the problem in and of itself. It says that the section of the lawn that Stewie mows, the red section, is supposed to be double the uncut section. And the uncut section will be the blue section. So the portion that is mowed is double the portion that is not. So the red is double the size of the blue. So what I could do is I could actually put numbers to that. I could choose any number I want to label the blue. Let's call the blue that it has a value of 5. Well, if it has a value of 5, then what's the value of the red? 10. And now I can work through some proportions. I notice that the cut portion is 10 out of a total of 15 when I put together the two parts. And I also notice that the uncut portion would be 5 out of a total of 15. Now, you wouldn't work with those purple fractions. Instead, what you would do is you would reduce that, and you would say that it is 2/3 and 1/3. Now, what I want you to do is I want you to take a look back at that green diagram and notice I could have went straight to the blue at the very beginning. All I'm going to do is I'm going to erase the 5, and I'm going to erase that 10. And instead, I'm just going to use the easiest numbers to work with. Well, it says that the red is double the blue. So that means if my blue is 1 part, then my red must be 2 parts. And notice what that means then is my red, the cut section, is 2 out of 3 total parts. And my blue, the uncut portion, is 1 out of 3 total parts. Now, you might look at that and say, okay, why are we bothering? But watch how much easier your algebra becomes. The function we could have built when we went through could have been that the shape on the inside is really just the uncut portion. So it is 1 out of 3 total parts of the total. Notice that my inside must be 1/3 of the total rectangle. And so now when I go through to expand that, I can expand the brackets on the left. And on the right side now, I have 600 divided by 3. Notice I miss out on all the ugly algebra. And maybe more importantly, I miss out on those risky mistake spots. I've avoided that. I could then go through and divide everything by a 4. And I love seeing that because that's going to factor pretty quickly. 2 numbers that multiply to give 100 and add to give negative 25. And therefore, we get down to a solution of 20 or 5. Okay, I take a look, 20 and 5, they're both positive dimensions. I should be good. However, take a look back to what x was. And if we go right back to our very original diagram, you'll notice x was the width of the pathway. And I just want you to imagine what would happen if the pathway was 20 meters wide. Hopefully you can see that we could not have this situation. And so therefore, I label my 20 as inadmissible. And to make sure that I finish off the problem, I put on the units. We're talking meters. There you go. Full solution. So keep in mind, we could have always went through and dealt with the big ugly algebra and did a direct translation. But I'm going to challenge you. When you come across a problem like this, play around with some of that ratio. It might really help out. Okay, there we go. Quadratic problems, day 1. Your job is to jump into your practice and get as comfortable as you can working through these problems. Best of luck.